Hello, my name is Przemysław Klubś and I'm a third-year PhD student in the ATOM group at the University of Oxford. Today I'd like to show you a quick introduction to PosgenPy, which is a Python code for finding the optimal parameters for cluster analysis from the ATOM data. First, let me go through the conventional method available in IVAS. For the purpose of this presentation, I will use one of my steel samples which shows some clustering of copper, nickel, manganese and silicon. In IVAS, we need to create a nearest neighbor distribution diagram to estimate the Dmax value for the next step. This requires us to select the solid ions, but also to assume an order value. The goal is to find a Dmax which gives us enough clusters that are real. In other words, the ratio of the randomized data to our real data shouldn't be significant. The problem here is that IVAS does this relabeling or randomization step only once, so this value might be different the next time we create exactly the same distribution. Next, we have to create a cluster size distribution. Here we have to find the n-min or the smallest size of the cluster that we include in the analysis. Note that any error in the previous step will be inherited in the next one and will lead to bad results. Step number 3 is the cluster count distribution graph, and in here we check how many clusters we have at different Dmax values using other parameters from the previous steps, which are n-min and order. Finally, we can use our selected parameters to run the maximum separation cluster analyses, and there are two new ones that we haven't checked previously. N, L, and the erosion, which you can't really pre-verify, just like we did with Dmax and n-min. So, as a summary, in the conventional method, we pick an order value, then find the next parameters, Dmax and n-min, using three graphs that might be different every time we create them because of this randomization or relabeling issue. And then to see if we can prove or verify our analysis, we have to manually go through this process again and again until we are happy with our results. Our goal with PosgenPy was to create an easy Python code which would automate this and make the selection of the final parameters for each sample more systematic. To make it easy for the people that are not comfortable with coding, we decided to use Jupyter Notebook. It is easy and at the same time transparent, so we avoided creating a black box. The user is asked to state a very small number of inputs and can see exactly how the data are processed. In there, the script will sweep through a selected parameter and create cluster pos files. Then it will automatically find the optimal n-min, which satisfies the 95% threshold of real clusters ratio, and plot how the cluster concentration of the selected solid ions is affected by the selected parameter, so that the user can make an informed decision based on the full matrix of analyses of the same sample. Let me show you an example. Here I wanted to know how Dmax affects my cluster analysis. So I created an array with these values, then PosgenPy created and analyzed required files, plotted the number of real clusters and how they will change with the different n-mins. Then found the smallest n-min that satisfy 95% threshold and created this graph where we can see how the concentration of clusters changes with Dmax. This tells us that there are no real clusters at 0.2 nanometer Dmax. N-min doesn't really affect this data, and there's no clear Dmax window at which the concentration would remain similar, or the slope of these lines are not flattening anywhere. So we either have to increase the order value or assume that there is no clear edge in the clusters, and as they have just nucleated and started growing and they're very, very small. To sum it up, PosgenPy offers not only time-saving but a more systematic and more correct way of selecting the parameters for your cluster analyses. It requires less user input than the IVAS method and allows you to make a more informed decision based on the comparison of many analyses made on the same sample. I'd like to thank Dan Haley and Andy London for the APT tools, especially Posgen, which made this code possible. I would also like to thank Dan, Andy, James and Hazel for the contribution to this project. If you'd like to use this code, it's available on GitHub. Thank you for watching.